Okay, the streaming has started. Okay. Okay, this is the third introductory lecture to the class of modeling and control of environmental systems. Up to now, we have discussed some general concepts concerning the procedure of modeling. We started by introducing our philosophical, or if you prefer, epistemological point of view, while we introduced the holistic and reductionistic perspective. And then we try to define the ecosystems as an object of research. Today, we shall go into more terminology, concepts that shall become common base for our reasonings. And in order to do that, I shall introduce you the general elements of a mathematical model. And then we will see later how these general elements play a role into the construction of an ecological model. What are the elements of a mathematical model? There are 5 fundamental elements. As we said, an ecological system or an ecosystem is a portion of space or time that is bounded or boundaried or presents a boundary, so that there are flows going inside and outside from the system. The outside conditions are described by what was defined external variables, or often we refer to these variables as forcing functions, because are the functions or the conditions that may change the behavior of the system. The behavior of the system, on the other hand, is described by the internal variables, what we call state variables. So the 5 elements we need to deal with when building an ecological model are, first of all, external variables, often called forcing functions, or sometimes control function. Typical example of this is the temperature T. Sorry, but I still have people that want to enter. They're not able. Okay. Example, the temperature T is the prototypical example of a forcing function, a control function. It is important to note, as you probably may already know, but temperature is one of the key parameters that influence the performance of biological processes, of course, of ecological, biological, chemical, physical processes, and so on. So the temperature, environmental temperature, that is a forcing function, so an external control to our system, is a characteristic that is fundamental in order to discriminate different behaviors of an ecosystem in different conditions. When we introduce these kind of quantities, it is also important to note, to define, or to go in depth into the understanding of a ranges of variations. For example, in ecology, we know that an optimal value of temperature for a wide class of biological processes is around 20 degrees. So 20 degrees reference temperature is, let's say, a starting point when defining the range of variation. Of course, living organisms have an optimal or an acceptable range of variation of temperature, meaning that below these values or above these values or above this range, ecological processes cannot be, or the biological processes are not performing in an optimal way. The second element of the model are the state variables. State variables display our picture of a system, maybe dependent or independent. Dependent state variables depend on the other independent state variables. Also, for this, you shall define and understand that they have a range of variations. The third element is that of equations, and we will go into detail about what we mean by equations. Generally, these are differential equations of various flavors. And then equations, it is relevant to know, important to know, that link external variables to state variables through what? Through universal constants, but in general defines the units of measures of various quantities that come into play, and through parameters. At different values of the parameters, you will have different behaviors of the model. So the parameters are the elements I may control or I may change in order to change the behavior of the model. We will discuss further parameters when we will introduce the process of model calibration, and we will see that in order to calibrate a model, we will act on the parameters in order to make the behavior of the model more adherent as possible to the real observations, to our analysis of a real system. So, 5 elements: external variables, state variables, equations, universal constants, and parameters. Equations link state variables and external variables through the constants and the parameters. So this is our first introduction of the element we shall consider when we are going to build a mathematical model of a living system or of an ecosystem. Let's go down now more a little bit onto the model types. We are making a kind of review of what we have already said in the last 2 lectures. The first important distinction is that between research and management models. Research models are tools for scientific investigation, while management models instead are applications that are of support for the management of living systems or for the management of systems under study. So research and management models is the first distinction. We already said something about research. Research models, we said already that management models all arise from research models, and research models typically come out from the interrelationship between analysis or observation and synthesis, so the mathematical formulation of the mathematical model. Then we have already introduced a very important distinction between deterministic and stochastic models. In a very rough way, we may say that a deterministic model display a defined, or if you want, exact output. So the output for a deterministic model is typically a curve, a function, for example, a function in time describing the evolution of a state variable. This is a typical deterministic output of a model. On the other side, we may consider stochastic models. In this case, the output values are more precisely described by a probability distribution. So, in deterministic models, you have lines or functions. In stochastic models, you have kind of clouds of values or probability distribution. Another important distinction is that between compartmental and matrix model. In compartmental modeling, state variables are associated with time-dependent ordinary differential equation. So, compartmental model is the starting point when you are able to subdivide the various actors that play a meaningful role into your ecosystem, and you start by introducing state variables, for example, the compartment of phytoplankton, or the compartment of zooplankton, or the compartment of mammals, or the compartment of nitrogen in the various form, or the compartment of phosphorus, or the compartment of inorganic phosphorus, that is orthophosphate, and so on. While matricial models are models by which the relationship between state variables may be described by matrices. And this is the first very useful way of starting to conceptualize the mathematical model of an ecosystem by normally introducing a matrix linking various state variables. We will see more about that later. Do you have any questions? No. Another important distinction from an epistemological point of view we have seen in the lecture of yesterday is the distinction between reductionistic and holistic model. I recall you that by reductionistic approach, we mean including as much detail as possible, and as a consequence, or if you want, as a side effect of a reductionistic approach, we may say that the behavior of the whole system is understood once we understand the behaviors of a single subsystem that make up the complete or the whole total system. In the holistic perspective, instead, it is based on principle of a maximum generality. We neglect several details. We prefer focusing on some general indicators that may be the energy or the entropy or the diversity or some other indicators that may somehow give you an holistic or a whole picture of a system by neglecting more some of the details that may be confusing, at least at the first step. Another very important distinction is that between static and dynamic models. Static models are models for which the state variables do not depend on time. So we write it mathematically by saying that the derivative in time of a state variable x is equal to 0. On the contrary, a dynamic model is a model in which at least there is one state variable that depends on time. And again, we formalize it mathematically by writing that the derivative in time of that state variable is different from 0. And the last distinction I would like to recall is that between distributed and aggregated parameters model. In distributed parameters model, parameters are function of time and position, while in aggregated parameter model, we have constant parameters within certain spatial temporal, certain spatial temporal extensions. Again, these are, if you want, very sharp-cutted differences: reductionistic, holistic, static, dynamic, distributed, and aggregated. In reality, when we deal with two models, we find ourselves dealing with some characteristics that are in between these two extremes, in between these extremes that we are stating here. In particular, a model may be reductionistic concerning some of the processes, while maybe holistic concerning some other indicators like goal function. So, for example, we may look for a global indicator of the behavior of a system. Example, again, the temperature is a global indicator of the state of a system. And in reality, the system may be in between static and dynamic, meaning that may be static for most of the variables, but we may include a dynamicity or some dynamics in particular variables. Which variables? The ones we are interested in, or the ones our focus is on. Again, same story between distributed and aggregated parameters. In the reality, most real models are in between, are somehow distributed for some parameters and somehow aggregated for some parameters. Okay? From a mathematical point of view of concerning the mathematical formalisms, we may immediately anticipate that distributed parameters models are in general described by partial differential equations. I have written here an example of a partial differential equation. A partial differential equation is an equation made up of combination of derivatives, first order derivatives in the spatial components and in the time components of the state variable I, and we say that the combination of these derivatives is equal to known terms, a function, again, a vectoral function of the vector x, y, z, and of a parameter t. These writings here include or implicitly assume that we are dealing with vectorial function. In particular, fi is a vectorial function, not a scalar function, meaning that fi has three components, one in the x direction, the epsilon direction, and z direction, and the first component that is related to the derivative of the parameter time. Aggregated parameters models instead are typically formalized mathematically in terms of ordinary differential equations. In ordinary differential equation, we take the derivatives of different degrees, first order, second order, third order, nth order derivatives in time of a state variable v, vi, and this combination is equal to a known term qi, that is, again, in this case, this is a scalar function whose components are e1, e2, e3, and so on. Okay, I think nothing new here. You shall have seen somewhere along your student career of these definitions. Then let's go more from a mathematical point of view into distinctions of model types. The first very important distinction is that between linear and nonlinear models. Linear models, remember, these are described by first order differential equations. First order differential equations, this means that we are taking into consideration only first order derivatives. In nonlinear models, instead, one or more equations are of higher order than the first. Then there is another important distinction that has to do with our epistemology. or our way of studying ecosystems or environmental systems. And this distinction has to do with causality. We talk about causal models in which input and output state are linked by causal relations, and this is the deterministic reductionistic approach. More often, we try to hide our unknowns or unknowledge of a system into what we call black box models. So in this case, uncertainty in the input are directly propagated or reflected into the output. So in causal models, we can find defined input-output relationships, input and output state relationships, while in black box model, we do not have this relationship, but instead we hide our our missing knowledge of a system by saying that some of relations are black box relationships, meaning we do not know exactly what are linked between input and output. Instead, we use essentially probability distributions that take into account uncertainties. In practice, most models are gray box in between causal and black box, meaning that for the relationships we know and we can apply, we use a causal relation, input-output linked relationship. For those aspects that are uncertain or for which our knowledge is very poor, instead we use black boxes description. And then a final but very important distinction is that between autonomous and non-autonomous systems. In autonomous systems, we say that differential equations do not depend explicitly on time. So we may write formally that the derivative in time of a state variable x is equal to a function that depends only on the state variable x. On the contrary, non-autonomous systems are systems in which the differential equation depends explicitly on time. In mathematical writing, derivative in time of a state variable x is equal to a function of the state variable x, and over time, so these functions may change in time. There are other distinctions between ecological models depending on the type of currency that is flowing to your model. The currency is the unit or measures, might be energy, might be entropy, might be concentration, and so on. Typically, in a demographic model, in which you have a kind of conservation of information, genome is propagated through a number of individuals. So the conservation law on which it is based, the demographic model, is the conservation of information in genetic code. Energetic models, so models whose the currency is flowing generally, are based generally on the very general principle of conservation of energy. I recall you that this is the first law of thermodynamics. In this case, the currency is an energy density, as for example, joule per cubic meters, while in chemical models, you have conservation of mass, based on the conservation of mass, we may build a chemical model whose currency, what is flowing over different parts of the model, is, for example, density of matter in the form milligram per liters. Okay, do you have any questions? No. Now let's start by the linear model matrix representation. But I have to silence all the people because every time somebody gets in. Ready? Stop your audio. Okay. Let's go to the first and more easier representation of models. Let us focus on linear models. In this case,
this is house.
oops, sorry, Kvali, but you are disturbing us. So now you are out. A linear model, it is typically described by matrices. So you have a matrix representation. For example, we may identify 4 elements of our system. So we identify 4 boxes, let's say 4 compartments, and each compartment is described by a state variable. x1, x2, x3, x4 are the 4 state variables describing the various compartments. One compartment may be, for example, chlorophyll. Another compartment may be nitrogen. Another compartment may be phytoplankton. Another one may be fishes, and so on. So depending on our conceptualization, we may subdivide our ecosystem into compartments. We give a name to each of these compartments, particularly by defining a state variable describing the compartment. For example, let's say that the 4th compartment is the compartment of phosphorus. So x4, so the state variable related to this compartment may be milligram of orthophosphate per liter, so density of matter. And then we describe the relationship between the compartments by drawing some kind of lines. A line here that is an oriented line says that there is some of the currency that is flowing from compartment 1 toward compartment 4. Please note that these are oriented arrows, meaning that these flows describe something that is getting out from 1 and entering into 4. The reverse would be described by an arrow with a reversal tip. So an arrow that starts in 4 and then ends 1. The easiest way for formalizing mathematically this kind of representation, as we have anticipated, is given by the matricial or matrix representation. In this case, we may write that the model or the evolution of our system is described by the evolution of a matrix A, in which we have a number. For example, A11 represents the flow or the strength of interaction internal recycling. In this case, A11 is represented by this arrow. Currency that gets out from 4 and enter back into 4. While, for example, A12 describes what is getting out from 1 and entering into compartment 2. We may extend this description to all the compartments of the model. Please note that these are oriented arrows. This means that the sign in this matrix makes are important. If you reverse the sign, you are reversing the arrows. And each one of these numbers into the matrix represent the strength of the interaction or the quantity of exchanges between the various compartments of the model. The matrix representation is very useful and very powerful because, for example, if we say that the state of my system at time t is represented by a vector of state variables, this is a vectorial equation, a vector of state variable I written as x at time t. In order to understand, or in order to calculate what will be the value of the state variable vectors at the subsequent time interval, I've synthesized it by writing t plus 1, but we may write t2 or something. So on a subsequent time, unit of time, you simply make the product, the multiplication in the algebra of matrices of the matrices toward the vector of state variable. And the result of this multiplication is simply the value of the state vector, state variable vector at the next time instant. This is a matricial product. So this is a row by column product, you may imagine. A is a matrix, while X is a vector. So this is a product of a matrix toward a vector. You, I think, have already seen this kind of algebra. This is a classical matrix algebra. And this way of representing the model is very powerful because from the point of view of the calculations or computational needs is the lowest possible. The algebra of matrix is a very powerful set of tools, gives us a very powerful set of tools for introducing kind of dynamical description of mathematical models of systems, complex systems. So now let's switch to the non-trivial problem of selecting the appropriate model for the issue you're dealing with. The selection of the appropriate model, of course, depends on the problem in analysis. For example, if our problem is a nutrification problem, then, of course, you will need nutrient concentration, chlorophyll A concentration, interaction between temperature and chlorophyll A production, and so on. So it will be a problem in analysis that will give you the first indication how to select the appropriate model. The second point is that of a target of a model. If we want to model a lake, for example, we will use concentrations of chemicals in the water column. If we are building instead demographic models, then a demographic meaning population model, then the indication is that the appropriate model should include a measure of a number of individuals. The first issue related to the selection of appropriate model is that of complexity. We have already talked about complexity. By now, you should be convinced that living systems are complex systems. And you may understand that given that we want to build a meaningful and useful model, we are going to select a model whose complexity is exactly adequate and not more to describe the system in analysis. In general, we say here that the complexity of a model or the complexity of our description shall be consistent with the complexity of the system I want to describe. Then at this point, you shall start discussing temporal and spatial scales. We already said these are very important, very relevant issues. The scales defines our level of the hierarchical level of our description. So it is exactly selecting different temporal and spatial scales, but I can focus my model at different levels. For example, if I increase the spatial resolution and decrease the temporal scale, my model will be more chemical process oriented. If I decrease the temporal resolution and increase the spatial scale, then my model will be more ecologically process oriented. Then a third criteria that should may guide you in the selection of the appropriate model is that of the availability of data. Availability of data in terms of quantity and quality of the data. It is useless to build an ecological model whose spatial or temporal resolution, for example, is seconds, and whose temporal resolution is seconds, if we have only experimental data or observational data whose resolution is hours or days or worst months or seasons. So the point is that the type of data that you have in hand will guide you in building the appropriate model. This point is very sensible because at this point I may get complicated. I may increase the complication or the complexity of a model without gaining any advantage in our understanding of the system. So the availability of data is a first guidance, the third, fourth guidance criteria that will help us in selecting the appropriate model. Then there are some peculiar characteristics, like, for example, if you need a model that it shall be able to perform some kind of structural dynamicity. For example, if in your ecological model you want to include the effects of invasive species, this means that you have to foresee in your model the possibility of adding a state variable describing the appearance of an invasive species. In this case, you may want to build a model that is able to include some kind of structural dynamics description. So, and then lately we have the question, we pose us the question, may we employ an object-oriented approach? For those of you that have some knowledge of programming, you know that the great advantage of object-oriented programming is that of dealing with objects whose ability of interact with the other object is already included to the definition of the object through the methods. You know, in object-oriented approaches, every object maybe, in our case, maybe an animal or maybe a phytoplanktonic cell. And for each object, you may define a method in order, or a set of methods that describe how you can gather information concerning the different objects. So the advantage of applying an object-oriented paradigm is that of including into a single element constituent of your model all the information needed to interact with these constituents and all the information needed to describe the interaction of these constituents with other elements. Okay. Then, in the selection of the appropriate model, we shall Those are some questions. For example, are we happy with a linear relationships model? If we are happy with a linear relationships model, then by now you know that we should formalize this model with the simplest possible approach, that is the algebra of matrices. So we are going to build a matrix model. Please note that linear models, as already said, are seldom adequate for describing ecological systems because biological or living objects often display some kind of nonlinear behaviors or catastrophic or explosive behaviors. Another question is, are we happy to describe our system with a stationary model? This is the case, in particular, if you have a limited availability of data and if you are happy or if you accept that this kind of approach provides an average response, for example, seasonal or annual or daily or monthly values. So we already, a point of selecting a stationary model or not is linked to the selection of the appropriate temporal scale. Then, in the case of limited availability of data, in which we describe our observation through clouds of probability, then we are probably happy if we build a probabilistic model. So we are going away. Remember, sorry, let me go back. I will just, we have dynamic. We are in between deterministic and stochastic model. So a probabilistic model is a model in which the aspects that are most uncertainly known are described by probability distribution, clouds of probability distribution. Then you may ask yourself if the model may be formalized by differential equation. This is, of course, the choice if you have a large amount of data of good quality and if you like to or you need to describe the evolution of a system in time and space. Of course, this is the model formalized by differential equation. It is two. I would like to formalize my model with different differential equation because in this case we have really a dynamic description of our system. But please consider that in this case you will need a large amount of data of good quality. Then you may ask yourself, as we already said, if you need structural dynamicity. Again, you need a large amount of data of good quality. But this approach has the advantage of shedding some light onto evolutive processes. If you are interested in describing some aspects of evolution, then you shall include the structural dynamicity because the object that are included into your model may change by evolution in time. And then the last question is, may be happy with an object-oriented. If you're happy with an object-oriented model, you may be happy, with an object-oriented model if you consider the individual as the base unit of a model. Typically, population dynamic models are object-oriented models whose objects are exactly elements of a population. Might these be animals or plants or certain forms of nutrients like nitrogen and phosphorus, like for example orthophosphates and so on. In this case, if you describe interaction between objects, you will be building an object-oriented modeling approach. So, in the end, by summing all these considerations, we may say that selecting the appropriate model means selecting a model with the appropriate complexity. And I will give you next week some tools in order to measure the complexity of a model. You have to take into consideration that the model is reliable as the least reliable of the inputs. So of course there is a limit, a bottom limitation of the reliability of a model, but it depends on the quality, the reliability of the data or input that you use for implementing your model. It is a matter of finding a reasonable compromise on the complexity of the different models. So it is a reasonable compromise between adding and taking away some aspects of the system, or adding and taking away some interactions between different actors of the systems, and so on. The focus in the selection of the appropriate model should be that of selecting the most simple model, simplest as possible, but with the minimum required complexity. Simple as possible meaning simple, but the model has to remain useful. So if you simplify too much, the model is not useful anymore. And this concept brings with it the concept of a minimum required complexity. So we have a bottom level, the minimum required complexity that you shall employ in order to describe the ecosystem under observation. Okay, an appropriately complex model will provide a better understanding of the system, meaning that your model will be not necessarily reliable in quantitative prediction, but you are more focusing toward a model with the appropriate structure, a model which includes all the aspects that you, the modeler, has decided are relevant for the description you want to implement. It comes automatically with this way of thinking, but we need a systemic approach, and that you need to keep in mind the fact that the model is not the reality, but instead it is an attempt to represent certain elements that are peculiar to the system. So the ecological modeler is not going to model the reality or the results of an ecological model implementation is not a real ecological system, a real ecosystem. Instead, it is a representation that tries to grasp certain peculiar elements of the system under study. So you understand why we said that the first step in the selection of appropriate model is that of starting from of a problem in analysis and then cutting out in terms of the target of your model. Now we finish this lecture. Today we finish this lecture by introducing the procedure to build a model, an ecological model. Please note that this procedure will be the subject of the lectures of next week, so we will go into details through various steps. The procedure to build a model starts from the problem definition. Example, I have noticed that this on the side of my field during hot climate starts to smell terribly. So I deal with a problem, for example, of how do you say, pourri. En français, on sait pourri. Comment on dit pourri en anglais?
Rotten.
Right, exactly. Rotten. So I have a problem that the ditches on the side of my field is displaying some kind of rotten processes, producing bad smells. And so I want to deal with this problem. Then, once I have a problem in mind, during problem definition, you really start throwing on the table all the elements. A field, a ditches, a problem of smell, climatic conditions matters, temperature or solar radiation matters. These are all aspects that you lie down during the problem definition step. Then you go to the second step, that is that of model conceptualization. Model conceptualization, you try to translate your problem definition into some kind of practical description of the system in terms of state variables or in terms of interaction and so on. Generally, model conceptualization starts with making sketches, boxes. A box is a state variable. An arrow describes the interaction of a state variable with another state variable. So you start really making some kind of drawings on the blackboard or on a white sheet. And then you start with an iterative process of adding and deleting elements and interactions between the elements of a model. Once you are happy with the model conceptualization, you are ready to translate your conceptualization into mathematical formulation. During mathematical formulation, you have having the conceptual model translated into mathematics, then you have the opportunity of verifying the behavior of the model. What does this mean? Verification of a model means analyzing the behavior of a model in order to be sure that the model is exactly behaving as you expect. For example, temperature increases, dissolved oxygen concentration decreases. If something different happens, then there is something, but it is probably not very well described into your model conceptualization. And so you have to go back to check and reformulate mathematically the model. Once you have a mathematically formulated and verified model, you are ready to go to the next step, which is that of numerical formulation. Numerical formulations means translating the mathematical formulation into, let's say, a computing language or into a computing environment or a calculation environment. This environment may be MATLAB, or maybe simple C programs, or Java programming, or maybe flowcharts, or maybe some other way to translate in numerical terms the mathematics or the equations that are describing the interactions between the elements into your system. So once you have the system described in terms of numerical formulation, then you are ready to go to the next steps, that are sensitivity analysis, and then calibration, and as the last step, validation. Let's see more in details. Problem definition, problem and data analysis. So what is the problem and what kind of knowledge about the system? At this point, you choose the limits and spatial, you choose the limits and spatial and temporal scales. So it is at this point that you define what are the boundaries of your system and what are the probably most appropriate scales in terms of temporal and spatial scales. It is at this point that you normally identify subsystems. For example, if let's stay in our model of eutrophication, a subsystem may be that of algae. I may include into my model a submodel or a subsystem in which I describe algal growth as a consequence of nutrient loads. Okay, this is a subsystem that is peculiar to my target, what is a eutrophication model. And then I go forward to the model conceptualization step in which I identify forcing function, identify state variables, identify functional relationships, design a kind of conceptual diagram, and particularly it is at this point that I study the suitability of the complexity of the model, suitability for the problem in analysis. So during model conceptualization, essentially we find forcing function for temperature, state variables, for example, chlorophyll A or nitrate concentration in the water column, identification of functional relationships, for example, chlorophyll A increases with increase in nutrients or nitrates, and then at this point I can draft a conceptual diagram, and it is on this conceptual diagram that I start making my calculation about complexities of a system. So once that I have a conceptual diagram, I am ready to start studying the complexity of a model and verify that the complexity of a model is consistent with the complexity of a system. I understand that now this sounds to you quite foggy. Don't worry, because next week I will show you that the tools that we will provide for doing this analysis are quite easy and straightforward tools. Okay, we go to mathematical formulation. What does this mean? This means writing equation for each relationship between the elements of a model. Identification of the constant parameters. I recall you that constants are relevant in order to cope with different units of the quantities that you're employing. So you need to include constants in order to be sure that you are not summing apple and pears. Instead, that we are summing apple with apples and pears with pears. So the choice of the constants has to do with this, while the parameters has to do with the possibility of changing the behavior of the model. The typical parameters, for example, in a eutrophication model in which you have a subsystem that describes algal growth, a parameter may be the rate of growth of phytoplankton. So this is a rate, for example, number of cells per unit time, or for example, concentration of chlorophyll I per unit time. Then, when you have identified constant parameters, you are ready to start dealing with ranges of variability of the parameters. For example, in the case of growth rate of phytoplankton, you are sure that you look into the literature, the growth rate of phytoplankton may be not higher than, let's say, 100 of cells of phytoplankton per second. It is really too fast, but it is also not slower when 1 cell of phytoplankton per year, but it is too low. It is in the moment in which you do a mathematical formulation that you identify the ranges of variability of the parameters. And then you go to the definition of the mathematical formalism. Mathematical formalism by now should be clear: ordinary differential equation, partially differential equation, or matrix formulation, and so on. Once you have the model, your model formulated mathematically, you are ready to start solving some of the equations so that you can verify that the model is behaving exactly as you are expecting it to behave. You see, the process of building an ecological model or a model of a living system is a kind of iterative process. You start from conceptualization, from definition, conceptualization, mathematical formulation, then you go back and you try to insert into your model all your knowledge or understanding of the behavior of the system you're studying, so that you can, in the end, verify that the model that you're employing is exactly including your knowledge. Again, the classical example: if in your model you have the dissolved oxygen concentration, then I expect that if the temperature is a forcing function of my model, I expect that by solving the equation, that the dissolved oxygen concentration should lower with increasing temperature. Okay. Once your model is verified, meaning that you have analyzed the behavior of your newborn creator, it's like it is like giving birth to a new born life, or to a new child. You start translating your observation and your knowledge in the system, of the system, into a numerical mathematical formulation, into a mathematical formulation what allows you to formalize your description to a numerical formulation, at which point you are ready to choose the programming language and the software by which you will run your model. So what you are doing, you are building a description of a living object, and you are building it into your small world, that is your CPU, your computer. You are putting into your computer all the instruction for building a model or a description of a real system. And this should recall you, as I told you a couple of days ago, but sometimes the mathematical modeler is so fond of his model that it tends to confuse his model with the reality. So it might happen that, for example, some researchers come to some conclusion, and when you ask them, why did you come to this conclusion? They say, oh, the model said that. Okay, the model said that, but at this point you have to be sure that your model is really verified, is really describing, including all your knowledge, and at your numerical formulation. So it's giving you some information, more new information of a newborn creator. You typically get in love with your child model, your childish model, so that you start thinking that he gets his own life and that he is a creature that is important to preserve. Once you have numerical formulation, then we go into the hard tasks of modeling procedure. Sensitivity analysis. Sensitivity analysis is the real first time you start knowing your newborn creature. Sensitivity analysis, you change the parameter, value of parameters and forcing function, and of whatever elements or sub-models or sub-components of your model, and you analyze the results of these changes. This is very relevant because it allows you to understand which are the key aspects of a model that you can control. Key meaning aspect that you change it just a little bit, slightly, and you obtain a dramatic changement of the behavior of a model. So during sensitivity analysis, what you do, you try to understand, to select, to sort out which are the parameters or the sub-models that are more relevant in terms of producing the final output of your model. Once you have a sensitivity analysis, then you are ready to calibrate. Calibrating a model means solving the equation and comparing the results of your model with experimental data and try to find optimal values of the parameters. Optimal, what does it mean? Those values of the parameters that make the behavior of your model more adherent as possible to the behavior of your target system. Once you have a calibrated model, you have a working tool that is formalizing your understanding of the system, a targeted system, into a research tool. And in order to obtain commercial product, you need to go to the last step of modeling procedure, that is called validation, in which you verify that your model is so robust, so well written that it is really representing some of the aspects of the processes or of the systems that you are studying in a consistent way. So validation is a confirmation of variation of parameters. Validation is verifying that our model applies as well to systems that are different from the system I have employed to calibrate the model. By starting from analyzing one system, for example, shallow water ecosystem, I pose the problem, I conceptualize, I formulate, I translate, I formulate a numerical formulate my model, I do sensitivity analysis, I calibrate my model on the system, then I have an object, a research tool that describes a shallow water ecosystem, shallow lake or a lake or shallow water ecosystem. And then with this tool, you apply this model to a different lake or to a different set of observations in order to see if the model still behaves or performs appropriately, even if applied to systems different from those employed for calibration. Okay. Okay, in the end of modeling procedure, the modeler starts posing us some tricky questions. First questions the modeler always asks himself is the model stable? What does this mean? Typically, when you do numerical solutions of complex differential equation system, what it might happen is that you might find yourself onto a boundary of a solution domain, on which if you cross the boundary, you have a kind of dramatic or very significant deviation of the behavior of your model. For example, in some cases, it might happen that your model is producing some kind of, let's see, please forgive me, I will try to make some pictures, but I'm terrible in drawing. A stable model will respond by providing for the state variable for a state variable, a kind of description. We have t on the horizontal axis, the value of the state variable in the vertical axis. So this is the t time axis. The vertical axis is the value of the state variable. In the case of a stable model, the behavior is better represented by a line that is bounded into the space of solutions. A non-stable model, on the contrary, let me see if I can change the color. A non-stable model instead may produce an output like this one, in which you have a derivation of a solution toward non-meaningful values, like for example, one of the state variables tend to grow indefinitely, or the reverse of a symmetric condition in which you have a state variable, but at a certain point drops to 0. The second question the model always poses itself is the model responding as I expect? This is exactly what I meant when I was describing you the story of dissolved oxygen and temperature. So I'm verifying that the model is including my understanding of the system. And then the last question the mathematical model typically poses itself is the model formally correct, or the formal correctness of equations? So is the mathematical formulation consistent when formally correct? I am using the right units for describing the various characteristics of a system. Okay, I think that by now we can stop here today. Let's see, do you have any questions? If you do not have any questions, in 10 minutes, I will, or 5 minutes, I will close the class, and I will see you on Monday at 10 a.m. Yaoundé time. Is it okay?
Yes, sir.
Are you happy with that? Are you able to download the average of my lectures from the website?
Yes, sir.
Very good. If you have any doubts or you just do not hesitate, contact me, write me, and I will try to answer to your doubts. Okay?
Okay, sir. Thank you, sir.
You are welcome. 2 minutes when I close the class. You can go out.
Goodbye, sir.
Bye-bye.
Goodbye, sir. Nice day, sir.
Yes, nice day to you too.
Goodbye, sir.
Bye-bye.